So welcome to session 2 of our series on LLMs. Our first session ended at the dawn of LLMs. So this session is really going to be the heart of the matter in really discussing LLMs, what they are, how they came to be. As a reminder, in the last session, we really talked about, we ended kind of on the note that if you looked at words in written text and considered them statistically, then you might be able to, start a sentence and guess how it ends. And we'll start from there in talking about what comes from there. So Sohrob, I'll turn it over to you as for the first stanza here.
Yeah, for sure. No, to keep things self-contained, just to recap this idea of a language model, what is it? What's its point? What's it doing? Ultimately, at some level, what we're trying to capture is something about the statistics and like likelihoods and probability distributions over sentences, words, and so on, right? Because there's something the hypothesis is there's something meaningful there. So, for example, when I say the cat in the, your urge is to say hat, right? And we can model that likelihood or that desire or whatever based on how often the word hat follows the cat in the, right? And there may be other completions, the cat in the room with the food in it, There's any number of completions, but there are going to be probability distributions over them. And there's different ways to model those distributions, right? So an n-gram, which was the sort of traditional way of dealing with that, would say, hey, let's count up the frequency of either the occurrence of the words, or if you're dealing with bigrams or n equals 2, let's count how often each of the pairs of words happens or each of the triplets. And as your n grows larger and larger, you get better and better abilities of representing and capturing and sort of poking at those sentences and making them do something useful, right? And so n-grams, obviously, as your n scales, now you're starting to store tons and tons of data that is sort of computationally, storage-wise, inefficient and intractable. And so there had to be a better way, right? Now, there's the history of neural networks sort of like waxes and wanes. It comes into popularity, it goes away, comes into popularity. But the neural network sort of approach to language models is to say, hey, let's take a neural network, which in some way at a hand wavy level mimics the brain. We'll feed in some sequence of words. And what we'll ask the neural network to do is predict the likeliest next word, right? So if I feed in the cat in the hat, right? The cat in the, I want the model to produce hat as the next output. And the way some of this works, just again, not to go too much into detail, but let's say each of the input layers is going to have basically as many neurons as there are words in the language, right? So when the is turned on, I'll turn on that neuron, cat, and so on and so on. I'll just turn on those neurons in sequence. Now, the way the neural network learns to do this is at first its random weights are going to say, hey, when I saw the sequence, I think this word should be the next most likely word. It's going to make a prediction. And what you do is say, no, we have a data set here. Hat was actually the next word in this case. Go back, change the weights in this neural network so that the next time it sees a sentence like the cat in the, it's more likely to produce hat as an output than some random word like zebra, let's say. And so over time with training, the neural network will start to approximate basically a distribution over your sentences, over your sequences of words, and it builds up a better and better model of the language itself.
Of the language itself, but really the training set, right? Because if you had, like in your example, if your training set excluded every book written by Dr. Seuss, then hat would not be the correct answer. And yet, if it consisted only of books written by Dr. Seuss, hat would almost certainly be the correct answer.
Yeah, this is an interesting place where bias is introduced because certainly depending on the data set you're trying to train the model on, it's going to have some reflection of the underlying training distributions that it saw in the training process, right? This is actually an interesting point because neural network language models have been used for a variety of tasks, right? So you could imagine it in the generative AI sense. I just want it to spit out likely sentences, right? I want it to produce language. Another case, though, might be, let's use it for machine translation. I want it to convert English to French, right? There might be another case I want to review, I want a model that can take reviews of products and say, on a scale of 1 to 5, how, positive is this review versus how negative. Each of these, what used to happen is you would train a neural network on each independent task-specific case. You'd say, here's our sentiment analyzer, here's our machine translation model, and so on and so on. You'd tweak the models a little bit here and there, but basically, you would fashion each model in particular use cases. Yeah. Now, what happened sort of roughly around the 2017 era, and that to a certain extent, this has been happening for a while now with neural networks and deep learning. There's always been this idea that just scale it up, make it bigger, make it, give it more data, and so on and so on, right? If you do those things, you're going to improve the performance of your model, right? And so the scaling sort of takes three possible sort of approaches. One is make the model bigger. Another is feed it way more data. And a third is just run that data through the model and train it over and over and over again. So roughly the amount of compute you give it. And these three things contribute to scale in a way that ultimately, in general, the argument was scale it up, it'll perform better.
Yeah, the question obviously always was, if you scale it up, will it perform better, but will it be the law of diminishing returns? Or if you scale it up, it'll perform better and it'll achieve some magical escape velocity, right?
Yeah.
And that was always kind of the question. It's like, yeah, if I double my cost of training and I get 2% more yield out of it, it's probably not worth it, right? But if there's some break point where I can eventually escape and get something entirely new.
Yeah, and this is precisely this has been the gamble with LLMs, and it turns out that actually it was a good bet to make, right? So LLMs, the way people are referring to it now is there's basically a scale at which you get these emergent properties and emergent behaviors and skills that these models develop that wasn't intended in the first place, right? So you'll also often hear these large language models referred to as foundation models, right? And ultimately, the idea is basically that scale it up, and you'll have all of these capabilities that you didn't expect in that model, and you can then maybe fine tune it for this task or that task, right? But you don't have to build these task-specific models built on task-specific data sets. Create first the foundation model, and then it'll apply to a wide range of tasks, right? And this process, in terms of scale, just looking at the size of the networks, if you take the neural network where we mentioned previously the weights in between each of the neurons in this model, if each weight is a floating point value that represents the strength of a connection between two neurons, that each of those weights is one parameter, let's say, right? In roughly, I think it was 2016-ish, 2017-ish, we're talking about 100 million, 2019, we're talking about models with 100 million parameters.
Which sounds like a lot, but in retrospect, turns out not to be that a lot.
Yeah,
right?
yeah, it's big, but when I remember in grad school, I was working on speech recognition, and they'd send you the speech recognition data set, the standard TIMIT, 700 megabytes on a CD-ROM, and you're like, that's huge, that's fat, and that's insane. But yeah, so 2019, you're starting 2019 with 100 million parameter models. You get to GPT-2, which is 1.5 billion. So you're scaling by an order of 10 to 15. 2020, you get the introduction of GPT-3, a bunch of other models, but GPT-3 is at 175 billion weights. And interesting thing is that 2022, you get the introduction of Palm and Megatron. Now we're talking about 500 billion weights, right? And there's an interesting thing here that we can go to in a moment, that even though these larger and larger models continue performing better and better on certain types of data sets, they don't necessarily always equate to better and better performance in the way we want a conversational bot to sort of interact with us and to sort of to be intelligent in a very sort of hand wavy sense. Now, sorry, I don't know if I lost your audio. I'll point out one thing that on the emergent side, what happens is people realize roughly around that time of 2019 with GPT-2, these models actually have a lot of capabilities that they weren't designed to have in the first place, and they started to really start researching those qualities and those aspects, right? So GPT-2 was very good at, like, given some text, let's go and autocomplete that text. It felt sort of toyish, but there were interesting cases as well, right? So in terms of emergent abilities, even though the model wasn't trained to do, let's say, summarization, you could give an input description that you wanted summarized, and then on the next line, write TLDR, enter, and probably because of training on Reddit data, forum data, whatever, on the internet, oftentimes TLDR is followed by a short summarized version of the text that precedes it, right?
And somehow it learned this pattern, right? That it's like, okay, text, TLDR, then a shorter piece of summarized text. So if you prompt it with a TLDR, you'll effectively coax it into giving you a summary.
Exactly. And so now with GPT-2, you're starting to see these, all right, that's interesting. Like, what's it doing there? I didn't train it to be a summarization model, but it's capable of doing that. The same is true with the natural language translation. Let's say we want to go from English to French. I've sent.
This is where you're going to defer to me to read the French part, but
yeah.
You start the English.
So one thing that somebody realized is that you could start with a phrase in a particular language. For example, I'm not the cleverest man in the world, but like they say in French, colon.
And so now I'll take the part of the LLM, which is, okay, I will now complete the sentence in French. So it's not actually translating the beginning of the sentence into French, but it's like completing the sentence and saying it in French is effectively the prompt, right? And the answer being, je ne suis pas un imbécile, which basically means I am not a fool.
Exactly.
So the LLM has gone as far as saying, okay, I know I want to say I am not a fool, and I know to translate it into French in saying so.
Yeah. And so now you can overload this model that's been learned to just autocomplete text. GPT-2 is autocomplete on steroids, but with these interesting properties, right? And so now if I wanted it in German, I could say the same English sentence and say, as they say in German, right? And now I have a model that translates languages, even though it wasn't trained specifically for that purpose. Previously, what you would have had to have done is collect all this training data that is, English text coupled with various other languages, let's say. So UN documents, books like Harry Potter that are in every language. And then you train, given this, source language input, let's predict on the output side, the likeliest target language output that would, correspond to that input. Now, all of a sudden, you've trained your foundation model, and without having to do any new learning. And actually, this is a thing that is really referred to as sort of in-context learning or zero-shot, one-shot, few-shot learning. Essentially, without examples, the TLDR case, just put TLDR, and it's all of a sudden doing this other thing. Sometimes you want to give it an example of, like, let's say I want a model that does sentiment analysis. I could say, here's an example. This movie sucks. Sentiment, colon, negative. This movie is great. Sentiment, colon, and then wait for the model to, that serves as the input. That's a one-shot example where I say, hey, this is the thing I'm looking for. You autocomplete this next piece. And so without going back and changing the weights of the model is quote unquote learning to perform as you're sort of nudging it to.
Within a given conversational construct, though, right? I mean, so you have to set that up each time. There is no memory of that conversation that then goes into the model and subsequently allows you not to use that as a prompt.
Exactly. Yeah. This won't change the model. It won't. So much of modern sort of like interfacing with LLMs is really what's the context that you're sort of providing the LLM, and how do we sort of nudge it into the right space where it's behaving as expected. Now, there is actually another way. If we wanted a machine translation tool, you could fine tune the foundation model. Take the foundation model and say, hey, we have a bunch of text that says, here's the English sentence, here's the corresponding French sentence. Let's fine tune the model, go and actually update the weights. And maybe now with a small amount of training data, we can really get much better at machine translation. You could imagine the same thing for security
It becomes a question of
information.
like you use a generalist to solve a particular problem, right? It may take more effort, it may cost more. You highly specialize a tool to solve a particular narrow problem. You're going to presumably get it at lower cost and higher efficiency and better output, but at the cost of having to build a whole bunch of special tools.
Mhm. No, exactly. And this is the sort you start to see here the foundational, what like foundation really means. Because like now this one model that was just general purpose in the beginning can be fine-tuned, developed for various domains. But there's another interesting thing that happens once these realizations start kicking in. GPT-3 comes out, right? And again, from 2 to 3, we're talking about 1.5 billion to 175 billion parameter jump. So people started saying, hey, are the capabilities in these emergent properties also expanding? Like the abilities in zero-shot learning, does it mean we can sort of like really just overload the prompt and basically get it to do whatever we want? And it turns out that scaling up to that size did increase the ability of those models to do zero-shot, one-shot, few-shot learning. But on top of that, an interesting thing that really made the models sort of much more conversant and feel sort of chat-like, right? Or conversational. Basically, the models were fine-tuned on instruction data sets where I've given you an instruction and this is what I want you to output. And then the use of reinforcement learning, which is another paradigm in machine learning, based on human feedback, really put these models into alignment with the way we want to use them, the way we sort of expect to talk and chat with an intelligent assistant.
Effectively adapt them to what humans want out of them, hence human feedback, right? Human feedback in service of what humans want out of them.
Exactly, and this is it's the reason it's called the alignment problem. Like this RLHF, reinforcement learning with human feedback, is handling this alignment where previously these models were doing autocomplete, really good at it. But let's say I was doing, I wanted this model to take my natural language description of a SQL query. If I wanted to produce the SQL query, I have to make it look like comments in the query that describe, what I want out of the query, and then maybe start with the select parameter, phrase select space, and then based on that input set, it'll know how to autocomplete to do that task, right? That's cool, but what the reinforcement learning with human feedback does is sort of nudge it to the place where you can say, hey, just write me a SQL query that does X, Y, and Z. I don't want to write the comments and the headers and da-da. You can have a more sort of normal conversation now with these models in a way that like makes them kind of human, right?
Yeah, adaptive to human need, which is not the same thing as adaptive to truth or adaptive to anything else. You could adapt them to a whole bunch of different purposes. But here we're basically saying we want you to behave like another human being might behave who was somewhat expert at this task that we're giving you.
Yeah, and it's this RLHF process that allows you to put up guardrails. So if it starts saying things that are really wrong, offensive, you can say no, like thumbs up, thumbs down. Remember, previously when we were learning our language model, you had to have an input-output pair. Like here's your input sentence, here's the thing you should produce as a result. Now we can just give feedback in terms of thumbs up, thumbs down. Here's my rank ordered preference for your outputs and so on. And those types of things are now able to be used to change the model, make it less likely or more likely to produce certain types of output. And we all of a sudden get this more conversational.
So we have we've talked a lot about kind of GPT and OpenAI and kind of that tech stack, but there's also kind of a lot of news now. You know, when you look at Google, they're making noise about their models, and both their specialized model and their very generalized models. You see Falcon, you see Llama, you see Open Llama. It sounds like this knowledge is kind of broadly getting kind of diffused through a whole bunch of different groups, and this feels like the renaissance of these models, not just OpenAI, but kind of across a broad spectrum, right?
Yeah, it's an interesting time to be in this space because it's moving very fast. There's every company that's doing large language models as a sort of focus is obviously trying to get their models out as quickly as possible. There are fine-tuned models in service of various tasks, right? So you can imagine LLMs for law, right? You want to do case law, you want to do research, you got to be careful again. There's a lawyer recently who cited in LLMs imagined or hallucinated cases and got in trouble for that. But obviously in our space in security, Google has at RSA announced SecPom, which is their large language model fine-tuned on security data. Microsoft's announced a security copilot, and competing with all of these are also there's these large sort of institutional players or whatever, but also a very vibrant open source community that's developing and quickly adapting these models to be able to be trained at larger scales, be competitive with these more standard and larger company sort of products.
So we'll end kind of teasing things out for setting up things for the next section. We have really two forms of renaissance, right? There's the renaissance of the underlying model creation, how big they are, how they're being trained, how generalized they are, how specialized they are. And then there's this whole renaissance on the application of those things to solving a whole bunch of different problems, including problems in cybersecurity, including, as we will talk in future sessions, things that we're planning to do with them. But it's at this kind of very interesting junction point where there's a lot of moving parts and a lot of actors, and we are doing a lot of experiments. And we'll talk about again what they can do, what they can't do, how you augment them, things like that will be part of our next session. So thank you for this session number 2 on LLMs, and we will look to get to a more discussions on this, and ultimately kind of narrow it down. By session 4, we will very heavily narrow this down into the cybersecurity realm. We've got one more session, kind of foundational session between now and then.